Okay, thank you. Today, first thing, we're going to have our geophysics slash astrophysics session. And the first talk in our session is going to be given by Jack Burns. I believe it's a remote talk. So there he is. Jack, can you hear us?
Yes, I can.
Good morning. All right, well, let me introduce the talk on the lunar far side, a science and exploration imperative. Take it away.
Great. Thank you, Renee. I am getting an echo here on this end. Let's see, maybe that will calm down here in a moment. Okay. So sorry I can't be there with you all in person. I would have loved to be, but we had an unavoidable conflict with another important conference. So I'm beaming in remotely today. And I want to talk about the lunar far side with you all. As everyone there can appreciate, neither humans nor robots have ever landed on the lunar far side. And that's really a surprise. It's shocking, in fact, given that this is the largest planetary body with respect to the Earth. In terms of proximity, the surface area of the lunar far side is almost 4 times that of the continental United States, yet we've never touched the surface in any way. So I'm going to argue today that indeed the far side is an imperative for both science and exploration. And the science I'm going to focus on is going to be mainly in astrophysics. So let me advance to the next slide here and talk a little bit more about why the far side. And I've already spoken to the first bullet point. Second, which I think is important, is the moon, and the far side in particular is going to give us an opportunity to exercise some of the technologies that are going to be necessary for not only exploring the moon, but Mars and other planetary bodies, particularly human robotic exploration strategies such as surface telerobotics. And those are going to be key. And before we venture further out into the solar system, the far side of the moon is tough because it does require a communication satellite to be able to communicate directly. It exercises more advanced technologies and also can make good use of the Deep Space Gateway. As was discussed, I think, earlier in the workshop this week, particularly by my colleague David Kring, the far side is a priority scientifically in the lunar geoscience, particularly the South Pole Aitken Basin, for a lot of really interesting reasons, but I'm not going to reiterate those since I'm sure David and others have talked thoroughly about those. Instead, I want to focus once again on the fact that the far side, with the moon being tidally locked, far side is always facing away from the Earth, and therefore it is in fact the only truly pristine radio quiet site in the inner solar system. And so it's ideal for doing low frequency radio observations of the early universe. I don't know if this thing keeps bouncing, but I'm continuing to try to bring it back. And so in particular to explore what's called the universe's cosmic dawn. This is the epic formation of first stars and galaxies. All right, Ricky, I may need some intervention here. The slides keep advancing for reasons that I'm unsure of here. So maybe you could help me stabilize this. So why do we need to emplace radio telescopes at all on the far side? Well, it's because the Earth is an impossible place to do observations down to the very low frequencies, down to 10 or 20 megahertz, that one needs to do to explore the full range of cosmology from the early universe. The Earth's ionosphere in particular is a corrupting influence on the radio signal through refraction, absorption, and emission. In addition, the ionosphere is both spatially and temporally variable, and that introduces a kind of flicker noise into the any radio observations that acts as a systematic or a bias. It presents basically a floor through which it's very difficult, if not impossible, to penetrate. And that floor is above where we need to be for the cosmology. When you combine that with the fact that all of these effects scale as the frequency to the -2 power, going from 100 megahertz down to 10 megahertz is 2 orders of magnitude worse. And so the Farside escapes that. What ionosphere is there on the moon, its plasma frequency is well below that we would pursue with cosmology. So it's effectively not there on the moon. Radio frequency interference, also another major problem. We're all familiar with the FM band, but throughout the band, from 100 down to 10 megahertz, is digital television transmission, satellite transmission. And I know from recent observations of a polarimeter prototype that we have, one of my PhD students has built, that even in what are thought to be radio quiet zones, the FM and the other interference is really quite severe. Going to other presumably quiet places on the Earth, you still don't escape RFI because the ionosphere bounces these signals around the globe. There's also reflection off the moon itself, space debris, reflection off of there, aircraft and ionized meteor trails. There's just really no place on the Earth that one can go to completely escape the RFI down to the level that we would like to go. So do you go into space? Well, if you go into LEO or even on the lunar near side, the brightness temperature, and radio astronomers like to talk about brightness in terms of an equivalent temperature, is on the order of 1,000,000 degrees Kelvin. And we need to be 8 orders of magnitude below that in order to do cosmology. So we need RFI suppression on the order of 80 dB. And that's where the Farside opens up these unique opportunities. All right, so let me advance the slides here. Then, and see if I can bring back the cursor here too. So the astrophysics community has done a number of surveys in which they've identified this cosmic dawn as a priority. In particular, the Astrophysics Decadal Survey now, going back about 8 years. Cosmic dawn was listed as one of the 3 top priorities in the Decadal Survey. Not a surprise. Try to understand the origin and evolution of the first stars and galaxies in the universe. More recently, NASA Astrophysics Division did a 30-year road mapping exercise and identified specifically both small and large missions associated with observing at low frequencies using the highly redshifted 21 centimeter line of neutral hydrogen to probe the gas around the first stars and galaxies. That's the nature of the observations that we do at low frequencies. So the small mission was a lunar orbiter or a single element on the surface of the moon. And a more visionary instrument was called the Cosmic Dawn Mapper, an array of thousands of dipole antennas that would begin to actually map structure and structure formation in the early universe. Deployment likely would come in stages. At the top, I suggest here surface telerobotics deployment, either with a small array or an individual element, followed by later, when we're talking about these thousands of dipoles, probably something that's more along the lines of an astronaut-assisted deployment. We've published a series of papers on these instruments, several of which are listed below here in Advances in Space Research. So over the last 6 months or so, our new survey team called NEST, the Network for Exploration and Space Sciences, has begun doing some trade studies on lunar telescopes for the Farside. And here's our trade space that we list up here that includes instruments, deployment, environment, power, location, RFI, and communications. And what I want to do is briefly go through those because they lead to constraints on where on the lunar Farside would we like to host these radio telescopes. All right, so let's start off with instruments. So I've already alluded to two forms of instruments. One that I'll call a hydrogen cosmology global signal telescope. So it's an all-sky instrument, just a single pair of dipole antennas like what you see here in this cartoon picture, operating down to maybe as low as 10 megahertz. The requirements here are relatively modest in terms of power, data storage, and data transmission, and all of this could be very easily facilitated through the Deep Space Gateway. The Cosmic Dawn Mapper is a much more ambitious telescope. The full design would be, as I mentioned before, thousands of dipoles, significant bandwidth, data requirements, and power. But this is not what you would put down on the surface to begin with. This is the final instrument. So you would build this in stages. You would build it in an evolutionary fashion, beginning with a few dozen dipoles, and there's some early science to be done that way, as shown in this cartoon picture of these dipole elements that we lay down as part of a polyimide antenna backbone. So we began then asking the question, where on the moon, where on the Farside could we locate? And of course, there's a lot of interest in the poles because of water and a possibility of mining water. So we asked the question, would it be possible to locate deep inside a polar crater and put the antenna in here, as you see in this cartoon picture. Here we go. Let me get my cursor back up over here. And so here's a cartoon of an antenna. We've actually put the receiver below ground here to both moderate the temperature as well as the plasma effects that Bill Farrell talks about a great deal. And the reason that you're located in here is that the radio frequency interference coming from the Earth at these low frequencies suffered diffraction effects. So the radio emission bends over the surface as well as structures. And for example, that's the principle behind the over-the-horizon radar, which operates at similar frequencies. It bends around obstacles. So can we suppress in a crater like this one enough of the RFI to be able to do the observation? So the cartoon picture shows the setup. This next slide shows you the calculation that we did. And it's a very simple calculation. In this case, we put a knife edge obstacle here that represents a crater wall. T sub x is the transmitter on the Earth that would be facing the near side, and the distance from the Earth, and d sub r would be the distance from the crater wall. And then we calculated what the attenuation would be. And this is very difficult. As you can see from these curves here, that each one of these curves corresponds to a different height, h, of the crater wall. And even going all the way down to, let me find my cursor again. Here we go. So even going all the way down here to a height of a crater wall of 10 kilometers and being right against the crater wall, you just barely get to 80 dB. There's several problems with doing that. Number one, you block off a good part of the sky. And secondly, there is significant interaction, as we know from our ground-based test instruments that we have built, between obstacles like this, a crater, the crater floor, and the beam. It does some corruption of the beam that makes the observations difficult. So the bottom line is we don't see it practical to find a crater that would have sufficient suppression at the poles to do the kind of observations getting down to the level that is really required. So where would we go? Well, what we've done now is we've done recently more sophisticated modeling. In particular, my colleague Abhi Datta has done an electromagnetic simulation of the RFI over the entire limb of the moon. And here what we're looking at, this particular piece of the simulation was done for a latitude of 80 degrees south, and we asked a question at a frequency of 1 megahertz, then how far from the limb would you need to be in order to achieve that 80 dB? And the answer is about 45 degrees from the limb. So this was not done arbitrarily. We were looking to see if there's a particular region on the moon that we're interested in that we could set up shop. And here's a cartoon picture of that region. So here in red and light red are regions excluded around the poles, as well as crudely drawn here some excluded region over to the western side of the pole over here. In particular, our target was to look at Schrodinger, which is a favorite spot that David Kring, I think, and his colleagues have made a very good case for geological exploration. So the bottom line in our simulations that we've done is that about half of the Schrodinger crater, particularly the north and northeastern quadrant, gets us to that 80 dB suppression. So this region in particular, I think, would be a good one for us to be able to set up shop. And that's nice because we can imagine both geological as well as initial radio observations being deployed with surface telerobotics. Just a little bit about the, the lunar environment, some of the obstacles that we have to face. As I alluded to before, there is interaction between the surface and the beam. So one of the things when we deploy our radio telescopes, we are going to have to map out the conductivity and the permeativity of the regolith in advance. The dust and the changes in surface electrical potential could be potential obstacles as well. Bill Farrell, Mihai Harani, and others have pointed out the surface potential changing by factors of 10 during, for example, solar energetic particle events, relating to also some dust elevation that Surveyor and Apollo astronauts saw. What this may require is us to remain grounded to the plasma, and I'll talk a little bit about that in just a moment. The elevated dust also could cause some visibility problems,
Jack,
not operational problems for the low-frequency antenna, but visibility problems in terms of teleoperation.
Jack, can you hear me?
Yes.
Okay, we have to start wrapping it up so that there's time for the next speakers.
I understand. I'm almost done.
Okay, great.
What we talked about over here, the last bullet, is that I think one of the things looking at in terms of deployment is mitigating some of these effects by putting some of the electronics underground and within a Faraday cage as well. I'm going to skip over the temperature issues and just last slide here on power communications. Power requirements for the initial array or the initial telescope are modest, can be, I think, facilitated, and some interesting work is being done right now looking at power beaming from the Deep Space Gateway, and the gateway, once again, can be used to help with the data transmission. So here's a summary and conclusions, just wrapping up, just summarizing all of the things that I had mentioned during the talk. So let me stop there since I'm running a little long, and be happy to take any questions.
Okay, I think we have time for one quick question. Sharon?
Quick question. So, as you know, the Lunar Geophysical Network, that's supposed to be on New Frontiers 5, requires us to have a geophysical node on the far side. Now, it'll be extremely challenging to combine a full cosmic dawn experiment with an LGN. However, my question to you is there any limited scope experiment that can help you advance the cosmic dawn science with a Farside LGN node?
Yes, I think that's a good question. And as I mentioned a couple times in the talk, the nice thing about this technology is it's very much evolutionary. So you can start off with a single element to do the global signal, pretty simple, pretty low power, and then evolve this to an array that gradually grows over time and becomes more potent in terms of being able, both in terms of signal to noise and scale that it can map. So I do think there's some synergy there that would allow us to start off modest and grow over time.
Thanks.
Okay, thank you, Jack. And stick around. If we have time at the end, we may do a brief panel discussion. Our next talk is Georeferencing of Landers and Rovers, Tests of General Relativity, and Metrics of Laser Retroreflectors. And Simone couldn't be here to give the talk, so the talk will be given by Orlando Luongo. Welcome.
Good morning, everybody. My name is Orlando Luongo. I work as a theoretical physicist in the field of cosmology in the INFN in Rome, the National Institute of Nuclear Physics. And as you can see, the INFN is affiliated with NASA survey, and our proposal to NASA is to consider laser retroreflectors for the inspection and for the study in the world's solar system. In particular, I will discuss on some applications in cosmology, that is my field, and the technique of lunar retroreflecting applied to cosmology and astrophysics, so using retroreflectors. The INFN is a joint laboratory with ASI, the Italian Space Agency, and we are working on microreflectors and Moonlight, which is a reflector which has dimensions larger than INRI, for example. In particular, my talk is divided into the study of Moonlight, INRI, and the use of PEP. PEP is a program, is a free available program, planetary ephemeris program, which could be used for testing general relativity and for understanding new physics. For example, for understanding if general relativity works fairly well in the solar system regime and at larger scales. When I say larger scales, I mean cosmological scales. So we are looking for frontiers of new physics for understanding if laser positioning data could be used for matching cosmology with solar system, with data coming from solar system regime. As you can see from this table, we are able to fix and to bound some cosmological but also gravitational parameters, such as the post-Newtonian parameter. We are able also to test the equivalence principle in both its forms, the weak and the strong ones. In particular, when I refer to the weak form, I refer to the quality of matter, and when I refer to the strong form of the equivalence principle, I'm referring to the quantity of matter, and in sense that if bodies fall down in geodesics, we have different accelerations and different terms which could be included if the equivalence principle is not valid. But also, we look at time variation of gravitational constant, of gravitational constant, the constant of Newton, since modern theories of cosmology implies the existence of dark energy, as you know, and dark energy probably could be obtained by using a time variation of fundamental constants. So, understanding if this variation could be found in the solar system regime would be useful for understanding if at large scales the dark energy contribute can be considered from such a point of view. But also we are looking at inverse square law Yukawa potential, which modify the Newtonian potential by including two additional free parameters different from the standard Newtonian potential. Here, for example, you can see a plot in which we have in a log-log scales the two parameters that I was saying before, alpha and lambda entering the Newtonian potential, entering the Yukawa potential, which extends the Newtonian one. As you know, the Yukawa potential is just a by-hand extension of the Newtonian potential, but some theories of gravity, some extensions of general relativity predict the existence of a Yukawa potential. So understanding if such constants alpha and lambda are different from the ones predicted by standard gravity, so in the weak field regime of Newtonian gravity, would be useful for understanding if f of r gravity or f of t gravity, for example, could be considered as the final paradigms for describing the universe dynamics. Lunar laser ranging, the technique of lunar laser ranging is also useful for synodosity. I'm not an expert of this field, so please apologize me. The lunar laser ranging provided the best data for the deep interior of the moon, for example. And our next generation of retroreflectors will strengthen the collaboration with GRAIL and also with the NASA versus Prospector mission, since our reflectors have been proposed as payload. This is the INFN President formal letter to NASA survey in which we ask for collaboration, just to show you this quick picture. And then our collaboration are now with those teams, for example, Team Indus, Moon Express 1, NASA versus Prospectors, and so forth. In particular, you can see here in the slide the collaboration with Team Indus. Moonlight and Erie mockups have been delivered to Bangalore on August 2017, and this is one colleague of us who was there for bringing the mockups. Now we are doing the qualifications for delivery of flight models, and in particular you can see here the mockups on lander deck placed with different angles to enable measurements by the orbiter. Also, the Moon Express mission, MX-1E, we have this collaboration for their mission. We have an agreement for their future mission, and we put on their lander the Moonlight and Indy reflectors. As you can see also by their website, for their first expedition, Lunar Scout, the first commercial voyage to the moon. Now it's the turn of physics, as I was saying to you before. In particular, we want to address by the technique of lunar laser ranging some problems relating to general relativity. You know that at large scales, at cosmological scales, we have two great problems. The first one concerns the existence of dark matter, so something which is missing in terms of gravitational interaction. And we have dark energy, which is something which pushes up the universe to accelerate. So we should understand the origin of such terms, and it seems that general relativity is unable to provide their existence because you have to add some new ingredients into the picture or into the Einstein picture. So for understanding how their origins come from and where they come from, we can imagine to extend general relativity. When you extend general relativity, you should have some new degrees of freedom inside the Einstein equations and inside the standard Hilbert-Einstein action. And you, for example, get the result of dark matter and of dark energy by means of additional degrees of freedom that in this case, in the particular case that I'm showing you now, are inside the modified equation of f of r gravity you see in the last equation of this slide. F of r consists in the fact that you replace the Ricci scalar, which is the main ingredient of Einstein gravity, by an analytic function of r. When I say curvature, r is the curvature, I say something related to the matrix, so something related to the space-time, which is useful for describing the universal dynamics. So when you consider that, you find an acceleration naturally, but you have some correction to the Newtonian potential. So the question is, are we able to consider the technique of lunar laser ranging by using retroreflectors to check the validity of such theories? And second, are we able to match cosmological data with local data coming from the solar system? The answer could be yes, if we consider the modifications of the equation, in particular the modification on the ppm parameters in the weak limit regime. If we take those equations, gamma and beta, we are able to expand, for example, in Taylor series, the f of r gravity, and then to relate the derivatives of f with respect to r in terms of cosmological parameters, which are q and j in this slide, the acceleration parameter and the jerk parameter respectively. This technique is known in the literature with the name of cosmography. And if we take this, we are able to match two different levels of measurements, the local and the large scales ones, putting inside the gamma and beta the results that we obtained from a cosmological point of view. So if observations, for example, by lunar positioning, are able to show that gamma and beta are compatible at cosmological scales with local scales with the ones predicted by f of r gravity, we will reach our goal to understand that gravity probably breaks down not only at the level of cosmological scales, but maybe also at the level of solar scales. This is something very important because we are trying to falsify gravity. That's something very strong also. So, but probably it's one of the most important goals of future time cosmology. In fact, together with the applications that we can do in the field of cosmology concerning the universe acceleration and the understanding of the time variation of the gravitational constant and the existence of dark energy predicted by a curvature effect. From prime principle, we can also try to find a solution to dark matter. In fact, the Newtonian potential, which was modified by Yukawa expression of it, as I told you before, is now inferred in the theories, in the f of r theories, I mean, in that form, as you can see, looking at the gravitational potential, which is modified, and alpha and lambda, the two terms which have been put by hand, as I told you before, are now degenerating between them, and you have to include also the first derivative of f with respect to r. So this result is very important because if we can constrain alpha and lambda, we have constraints also over the quantities entering in the equation. And those quantities could be also constrained from a cosmological point of view, again, in spiral galaxies, for example, looking at the velocity with respect to the radius in spirals. And we have to remember that the Milky Way is in this group of galaxies. So time variation of G is also counted here. I come back just a few seconds. When you consider G effective, which is the constant of Newton over f prime. Again, you have that f prime enters the modified potential, and so the results coming from the positioning that we can consider from lunar retroreflecting technique could enter also this gravitational picture. So, summing up, in Frascati, in Rome in particular, we work on modeling moonlight and IRRI, our two reflectors. While moonlight is a USA-Italy collaboration, IRRI is just Italy only. In particular, we work on understanding by simulating data and by simulation in general, if general relativity works fairly well at the level of solar system, by using the free available program PEP, the Planetary Ephemeris program, but also we are looking for new physics, and in particular for understanding if general relativity could be extended by extending theories of gravity, modified gravities, and if at the level of solar system we can match those results with cosmological scales. And that's our main goal, probably one of our main goals from a theoretical point of view. Thank you.
I have a question about your talk in terms of where on the moon are you going to put these retroreflectors, especially relative to the ones that are already there. Where do you want to go?
Where? Okay, that's a good topic. A technical topic concerning exactly the point in which we want to go is not exactly my business. Sorry, you should ask Simone. But anyways, I can say that the far side of the moon, as we discussed it before in the first talk, would be interesting, for example, for understanding some signals coming from the external part of the universe. So if we have an orbiter who is able to measure at that, in that point, for example, in that region, it would be useful for us for a better positioning and a better data acquiring.
I think we're all well convinced that there's exciting physics to be done with the retroreflectors, but I think what you need to tell us is what's the mass of the two varieties of retroreflectors?
Oh, the mass, you mean the weight of...
right, if we're going to stick it on a rover or a lander.
Erie is so small, I can show you a slide. Doesn't work. Okay, I can't. At the very beginning, you can see that moonlight is 1.5 is a 4-inch diameter reflector, while 0.5-inch diameter reflector for INRI. So the mass is extremely small in both cases, since moonlight is something like kilograms, while INRI is something like grams. So the orders are very small, and so they do not influence the analysis by themselves. Okay. Thank you.
Thank you. Okay, our next talk will be given by Seiichi Nagihara. He will be talking about in-situ heat flow measurements in the Maria outside the PKT. Seiichi?
Okay, thank you. Okay. Here you go. I guess I need to get used to this. Okay. Good morning. The astronauts on Apollo 15 and Apollo 17 were able to successfully deploy heat flow probes. So we have 2 measurements so far on the moon, and then, so that's it. And the picture here is, let me see, here you go, yeah. Was taken by Jack, the Apollo 17 LSEP site. As you can see, so there's probe 1 and probe 2 of heat flow. So the astronauts drill holes and install these probes. Let's see. So the heat flow probes deployed on the moon actually determine heat flow as a result of 2 separate measurements of thermal gradient and the thermal conductivity of the regolith penetrated by the probe. And so in making measurements like this, it's one of the things that's important is you have to install the sensors deep enough so that it can avoid the influence of the seasonal and diurnal temperature change at the surface. So that the depth of the reach of those surface temperature change is called the thermal skin depth, or the skin depth. For the moon, it's about 1 meter or 1.5 meters. So as you can see, yeah, Apollo 15 kind of barely made it. And for Apollo 17, they actually redesigned the drill. So that's why they had a relatively easier time reaching the target depth of, 2.5 meters. All right. So the geothermal gradient is obtained basically a temperature measured at different depths, so that gives you the thermal gradient. So anyway, so the Apollo 15, the heat flow was determined to be 21 milliwatt per square meters. Oops, it just keeps changing on me, I'm sorry. Then Apollo 17, 16 milliwatt per square meters. All right. So then fast forward 25 years. So the Lunar Prospector returned the data from its gamma ray spectrometer. So that revealed the surface distribution of the so-called heat-producing elements, thorium, uranium, potassium. So then they found that so basically there's an area with high concentration of these heat-producing elements. So those were later defined as the PKT, right? Then, so at that time, it's been suggested that the heat flow values at Apollo 15 was a little bit bigger, so mainly because Apollo 15 site was located in PKT. So So that suggests that maybe there's more heat production going on there within the crust. So that may be the reason that you got higher number at the Apollo 15 site. All right. Then, so in thinking about doing more additional measurements on heat flow, I think we need to kind of dig in a little bit deeper into that hypothesis. So just in order to illustrate that, I'm going to borrow a picture from Renee's paper here, and so we are measuring heat flow that is escaping through the surface of the crust, right? So that's the QS there, right? So the amount of heat we are actually capturing may not be the same as the heat flowing up through the deeper part of the mantle, right? So because the reason for that is, again, so we have probably heat generation going on within the crust, right? Then yes, we know the surface concentration of these elements from gamma ray spectrometer measurements, but we don't really know their vertical distribution, right? So the expectation by many scientists is that probably there are more heat-producing elements within the crust compared to the mantle, but we don't really know how their vertical distribution changes. Again, the expectation is probably they decrease with depth, but again, we don't have a very specific numbers attached to them, right? Then also this vertical distribution even within the crust may also vary geographically, depending on the terrains you're looking at, right? So that's why in thinking, what kind of additional heat flow measurements will help. So my thinking is we need to go to a place far away from PKT. Then so way we can expect the heat production within the crust is relatively small, so that basically what we measure at the surface will closely represent the so-called mantle heat flow. So that's the heat flow that flows out of the mantle and into the crust. So that may help us better constrain the thermal structure of the deeper interior of the moon. Here you go. Then also now we know from the GRAIL missions that the thickness of the crust varies quite a bit on the moon. So in like a big mare basins, the crust may be as thin as 10 kilometers, right? Then, but in other places, the crust may be as thick as 60 or 70 kilometers, right? So there is also a chance that the total amount of heat production within the crust may also vary geographically with the thickness variation of the crust, right? So thinking about these things, so what we are suggesting is that, so we go to mare basins where the crust is known to be very thin, right? And also they're far away from PKT. So if we make those heat flow measurements at those places, probably we are targeting the places where the heat generation within the crust is relatively low, so that's why we have probably better constraints on the mantle heat flow. Then, so by knowing the mantle heat flow, we may be able to better constrain the thermal structure with the deeper interior of the moon. Then, so we're suggesting Crisium and Nectaris, mainly because, again, they are in the mid-low latitude of the near side, so that's why they are more easily accessible than some other basins. Here you go. Then some of you may argue, so what about the Apollo measurements at Apollo 17, right? So Apollo 17 measurements are outside PKT, so that should represent maybe, the cool part of the moon. But some more recent studies suggested, like for example, so the Apollo 17 site may not be far away enough from PKT, so there may be some thorium-rich ejecta lying there. And then also, so these pictures are from Paul Warren's paper, from 1987, showing that so the Apollo 17 site was a sort of located at the edge of a basin where you have a sharp geologic variation in the lithology. So when you have a spatial variation in lithology, so that also translates to spatial variation in thermal conductivity. So because of that, we may be getting we may have got some kind of edge effect at the Apollo 17 site. So that's what Warren and Rasmussen papers are about, one of the things they talked about at least. So that's why, so the measurement at Apollo 17 may not represent a sort of a typical value for the cold part of a cold mare basin. So if we're going to make a measurement in the mare basin, then we probably should target some central, flat, very homogeneous part of the basin. Then, so that's the place we want to go. Then also, we have to have an instrument ready to go. So that's why I've been collaborating with Honeybee Robotics for the last several years. Then we got PDIP funding several years ago. So we were able to develop a sort of mid-TRL prototype of the heat flow probe, specifically for robotic missions to the moon. Then, so it's very small. It's about 2 kilograms. Our current prototype weighs only 2 kilograms. Then it's about the size of a shoebox. All right. Then if I can get the, oops. Okay. I don't know if I can get help getting this video on the lower left going from the back there. Oh, here you go. Yeah. Okay. Thank you. So we have this a fiberglass tube that spools out, like you see. Then at the tip of the tube, we have a penetrating cone. Then at the tip of the cone, we have this needle sensor that makes the both temperature and thermal conductivity measurements. So the idea is basically we penetrate into the subsurface and make a stop like every foot and make the temperature and thermal conductivity measurements on the way down. Then of course, that mechanism alone doesn't really go very deep. So we have a gas jet coming out of the tip of the penetrating cone. So the cone kind of loosens the regolith, then they blow away the loosened regolith. So that seems to work pretty well. Then so that's on the picture on the left kind of gives you the idea. Then again, I wonder if I can get here you go, yeah, video going, yes. So we've tested this in a vacuum chamber. So Honeybee Robotics is like 3-meter tall vacuum chamber. So we had a big barrel of JSC1A simulant, vibrated and well compacted. Then we just blew it away. So we penetrated 1 meter in 1 minute. So we tested as deep as about 2 meters. So I think I think we're on the right track for that. So if we have another chance for further mature this technology, I think we'll be ready to go. Yeah. Here you go. Yeah, it gets really messy after the experiment every time. So what I have to do is actually use the mechanism in reverse, then use it as a vacuum cleaner to suck up all the regolith afterwards. So. That's my next, development. But yeah, here you go. So conclusion. So for additional heat flow measurements, we recommend central locations in the major mare basins away from the PKT, and such as the Crisium and Nectaris. Again, I'm not really dead set on these 2 basins, but again, so those are again on the near side. Then so they're relatively easily accessible, right? Then heat flow in these basins may closely represent the flow out of the mantle, which is useful for constraining the thermal structure of the deeper interior of the moon. Then again, both the Crisium and Nectaris are located in the near side, and they are wide and flat basin floor. Then I'd like you to also point to the, again, the companies who are sending the probe, the landers soon. So heat flow measurement does not require sample return capability. Right, so the heat flow probes can be accommodated into a variety of lander designs. So our instrument is a modular design, so that's why it's very flexible. Then, like I also said, it's very light, right? So discussion yesterday, there was quite a bit of discussion about where what's doable in the near term and what's more ideal, right? So in terms of that discussion, so the heat flow measurements may be very well suited because, again, it doesn't require sample return capability. You can accomplish everything in the near side, right? So that's why I think those traits are suitable for early stages of missions planned by private companies. Thank you for your time.
Thanks, Seiichi. I do have one quick question.
Okay.
Can you talk a little bit about how the heat flow experiment fits in with the Lunar Geophysical Network and the amount of, how long of a duration measurement do you want to make and that kind of thing?
Okay. So the heat flow instrument was listed as one of the top payloads for the Lunar Geophysical Network. And so naturally, if we can get more measurements at different places, that's better. Then, so in terms of the duration of the deployment, ideally, so like the Apollo did, like 2 or 3 years of deployment will really help to monitor how stable the temperature we are measuring at the different depths would be. Then, but basically in this design, we can make the actually subsurface measurements fairly quick. So that's why, so the deployment takes about only 1 Earth day, not the lunar day. All right. So that may be, again, so that may still be relatively lesser quality than the long-term deployment, but that still be probably, again, just if that's what we get, then we're happy to get it. So, okay.
Great.
Yeah.
Okay. Do we have any other questions for Seiichi? Okay. Thank you. Thanks again. Our final talk in the geophysics session is going to be given by Matt Siegler remotely. So as soon as I see him pop up, I will allow him. Matt, can you hear us?
Yeah, I can hear you. Can you hear me now?
Yes, we can hear you. Okay, so Matt is also going to be talking about heat flow, and the title of his talk is Lunar Global Heat Flow, Predictions and Constraints. So, Matt, take it away.
Okay, and thank you, Seiichi, because I think we have a lot of the same conclusions, and it's fun to see all that work, too. So this is work I did, and then with Pierre Williams and Dave Page at UCLA, and then we'll talk some about work with Zhangking Feng, who's at the Chinese Academy of Sciences that came and visited on a CSC scholarship. Okay, so we have 2 data points of heat flow from the moon, right? Well, okay, we only have 2 data points, but at least they're representative. Well, actually, as Seiichi just pointed out, they might not be, right? So later, after the Apollo missions, we discovered that PKT existed, and that there was a large thorium-rich, uranium-rich, potassium-rich province in this area of the moon. And it would be great if we could get future measurements away from this giant anomaly on the moon as far as heat flow. Okay, so that's the conceptual overview, is we have this large anomaly that is affecting the Apollo 15 and 17 heat flow data. And how can we use all this new other data, like the measurements of thorium and uranium from orbit, from Lunar Prospector and a couple other missions now, the crustal thickness from Grail, and I'll talk a little bit about the Changi microwave radiometer and some of the hope that that has in constraining some of these data. Okay, so we have these global maps of thorium, for instance, which we can then relate to at least what the surface, the top meter, is as far as radiogenic abundance, and then we have to make some assumption on how that abundance differs with depth. We have crustal thickness, which again has some variation and would be great to tie down with a landed seismic network. And then we have these orbital measurements in the microwave that give us some interpretation of subsurface temperatures. Okay, so what do we do to make a forward model of global heat flux? We basically take the thorium abundance that we see on the surface, get a uranium and potassium ratio to that to create what the radiogenic volumetric heat production of any particular spot would be. Use the Grail crustal thickness, and we can make a nice map of what we think the surface heat flux would be like under different assumptions. And what I mean by different assumptions here, I'm talking about changing the distribution of those radiogenic materials within the crust. So here we're taking a combination of regular crust, which is defined back in Wazorek and Phillips 2000, and we're mixing in some portion of surface material. For a lot of the talk here, can you see my pointer? No. Now, with this one. Anyway, there. Now you can see this line here going through the Apollo 15 and 17 sites. We're going to show a couple plots along that cross section. So here, for instance, is mixing different models of radiogenic abundance, where you would use either 100% of surface or only 10% of surface and 90% of the crust is contributing to the radiogenic heat. And you can see we could get a large variation in what we would expect as heat flow across the moon. All these models are using a 4 milliwatt per meter squared background heat flux from the mantle, but changing that would just like move this whole curve up and down. What we could do then is, if we assume we know, the mantle heat flux is something like that, we can start to constrain which models might be appropriate. So we can get some of the mixing of the distribution of these radiogenics through the crust from the Apollo 15 and 17 data already. We could start to constrain those. and we could see what areas might make a big difference or a little difference on understanding this model. So as Seiichi was saying, right, there are some places like these, I guess this is the Mare, these low spots are these mares, or this is the highlands and the Farside in general. We don't see much variation between the models. Right? It's basically in a radiogenic rich area. It depends, where you have a lot of surface radiogenics. Depends how you mix those through the crust, but in a low radiogenic rich area, you can actually start to constrain mantle heat flux. So we want to know what the lunar mantle is made of. Exactly, we go to one of these areas that we have these very tight constraints where all of our models would essentially predict the same heat flux. And so we could see how this curve as a whole would move up and down. And that would tell us what the lunar mantle is, and that's nice because then we can learn about the Earth-Moon impact and the formation of the moon and all that great stuff. There's some difference in models based on crustal thickness here. And so this is just using the maximum or minimum Grail crustal thickness models, and you can see there's a little bit of variation between the two models. But having more precise crustal thickness, which the seismic data will help constrain, will help with this, but it's not going to change it dramatically. Okay, so now we could see where on the moon we might want to land to help constrain this. So we saw that in highly radiogenic areas, we saw the biggest variation with the different models, right? So here, for instance, these two models with 10% or 100% surface radiogenics causing the heat flux, we saw a huge variation in a highly radiogenic area. Whereas, and so if we want to know about the composition of the crust, we actually want to go to the most radiogenic, highest heat production area we can find, right? Because that will actually help constrain what the crust is made of, how these materials are distributed through the crust. And then if we want to know about the mantle, we want to go to a place where we have the least crustal influence. And so that's where I might suggest a highly radiogenic spot and then a low radiogenic spot. And these are just the most extreme ones, where the difference between the two models was the lowest or the largest. And so those might be two possible spots. But again, we're not wedded to any particular one, but basically somewhere that has high radiogenics and somewhere that has low radiogenics seem like a smart way to approach it. Can other data sets help? We have this exciting measurement from Diviner, which we're finally getting around to publishing, where we have measured the temperature down to 18 Kelvin near the pole of the moon, near the south pole of the moon. This is in the dead of winter, and this seems to be constraining the crustal heat flux in a very low radiogenic area, sort of similar to one of the areas that we'd like to land in, down to something around 5 or 6 milliwatts per meter squared coming out of the surface. So this, in some sense, might be a hint at the constraint we're looking for. But certainly not as good as a landed measurement, because this is just an upper limit, because there still could be some sunlight bouncing off the crater walls and adding heat to this. There's another useful data set for global geothermal heat production that we haven't really tapped yet. I've just started to look at it as the Chang'e microwave radiometer. So for those of you familiar with thermal data, you can see this is sort of similar in effect to what a thermal map would look like. Here's the 4 channels between 10 centimeter wavelength and a little less than 1 centimeter. The text didn't come through here, but basically we have each of these wavelengths can see some penetration into the subsurface, so we're actually seeing the heat emitted from some column abundance in the subsurface. And how deep that column penetrates into the subsurface depends essentially on how much titanium is in the surface. So the loss tangent of the lunar surface. So this is similar to what Jack was talking about earlier. So something we can actually now potentially constrain with the Chang'e data remotely. So you can see how certain models of that loss tangent would change as a function of titanium content. And so you can see in a low titanium area, you actually can see deeper temperatures. In a high titanium area, you see temperatures near the surface. So what that means is that with a low titanium area, if you have different heat fluxes, so here's just a nominal equator model with different heat fluxes, you can actually, in a low titanium area, so the orange line here, you can actually expect a variation in 20 milliwatts per meter squared will actually give you a 1 Kelvin brighter brightness temperature than you would expect. This is for the 3 gigahertz channel, for the 10 centimeter wavelength channel, the longest one they had. And so we can actually take the data and take out the latitudinal variations. We could take out slope variations. We can take out variations from albedo because, right, the mare are darker. They're going to be warmer as well. If we take all those into account, we're sort of left with this map, which I would say is the extra heat that we can't account for from the sun. And this is interesting because you get a lot of extra heat in some of the areas that we're seeing as high thorium abundance from lunar prospector and from our heat flux map. So I've just gone ahead and sort of kludged together loss tangent effects of rocks and buried rocks, which I'm getting from mini-RF, EPR data, put that all together into a model. The model includes titanium, right? So here you can see high titanium areas, like these mare here. Trincolatatus is very high titanium. Will appear cold because you're not seeing very near the surface. And these are data at midnight. I'm sorry, I didn't reference that before. But basically, the gist is I can make a model of what, given everything I understand about the lunar surface and the geothermal heat flux, we can make a model of heat flowing from the interior. We could compare that to the data. And just to show you, if we had uniform global heat flux, this is what the model would output. So I think what we're seeing is signs that a microwave instrument like this in orbit could also really help a landed mission as far as building a context of connecting these landed data points. And so a slightly longer wavelength orbital instrument might be a great thing to add to a landed network of measuring geothermal heat flow. Okay, and then just there's a couple interesting things. If you do data minus model, there are a couple of interesting regions that pop out. If it's blue here, it basically means that I'm seeing more heat from the data than I expected from the model. So you can see here's Aristarchus, Marius, and this is Wolf Crater. There's some interesting areas that might be hiding extra geothermal heat flow below the surface that we can't see in the GRS data, which is only telling us about the top meter. So the thorium-rich materials in these areas might be covered with pyroclastic deposits or something like that. So anyway, there's a big model of what the eyeball best fit geothermal heat flux should be. We should go to the moon and prove if this map is wrong or right, and we can pick particular areas to constrain it better. And I'll end with that, so let me know if there's questions. Thank you.
All right, Matt, I do actually have one for you. I think you said all your models assume a uniform heat flux coming out of the mantle. Is that correct?
Yes.
Have you looked at any of those
models?
models?
I assume 4 milliwatts per meter squared, sort of based on guesses of mantle composition and the mantle volume.
Have you looked at any models that have maybe a global dichotomy in heat flux coming out of the mantle? Just out of curiosity.
No, I haven't included those or anything like that yet. There's some variation with from a paper by Matthew Landville that looks at what's effectively a mantle plume below PKT, and you get a little bit higher heat flux on the edge of PKT from the mantle, but otherwise the uniform heat flux isn't far out.
Okay, does anyone
But
else?
there might be a way to see if there's hotter temperatures under the PKT, which is something that some other work we did hints at.
Right. Okay, well, thanks, Matt. And we're pretty much out of time, so don't think we're going to have panel discussion for our geophysics and astrophysics speakers.